Okay. So, any questions? What I will do is, I will try one other very simple one so that you get a sense of exactly how things are going, and you can help me trying to solve this problem, and hopefully you will get a better understanding of exactly what is going on. Okay? So, let us just try one other very simple one. We will choose these problems, the subset sum problem and the set partition problem. I am going to assume that one has been proved by other people to be NP complete, and we will try to prove that the other one is an NP complete, and then we will flip the story, and you will see that depending upon which direction you are going, the transformation might either be easy or might be difficult. Okay, so, let us look at subset sum, which is essentially going to give you a set S and a number x, whereas the set partition problem is simply going to give you a set S. Which in your opinion would be the easier one to do? Meaning that, is it in your head the case that if I said assume that the subset sum problem has been shown to be NP complete, prove that the set partition problem is NP complete, or do you think that if I said we have found that the set partition problem has been proved to be NP complete, prove that the subset sum problem is NP complete? Let me tell you how I am thinking. I am basically saying that subset sum problem seems to be a little less constrained than the set partition problem. Okay, the set partition problem is not giving you access to this extra number so that you can collect to add up to be anything, whereas the subset sum problem is saying, hey, you have to split it into two exactly equal pieces. If that is what is happening in my head, then I am saying that because this looks a little more general to me, I think that this can be shown very easily to be at least as hard as this one. So, what I am saying is, I think I can prove this very easily. But if I can prove this very easily, what I am basically saying is that if you can come and tell me that somebody has already shown that the set partition problem is NP complete, I can show you that the subset sum problem is NP complete. So, I am saying that this one is the easier one to show. This is going to be slightly more difficult to show. So, let us look at this first. You are given a subset sum problem, a set partition problem which you know is NP complete, and you are asked to prove that the subset sum problem is NP complete. What has been given to you is, out here you will be given a set S. You have to produce a new set, and in this case a number, such that if there is a subset here that sums to that, then the set partition problem's answer is yes. And if there is no subset of S tilde that sums to x, then the set partition problem's answer is no. The subset sum problem is you are given a set of numbers and an additional number, and you are asked, can you take a bunch of these guys from this set, add them up to produce this number? That is the subset sum problem. Set partition problem is you are just given a set, and you are asked, can you pick out a bunch of numbers and take the remaining guys. So, essentially you partition the set into two pieces such that the sum of these guys is the sum of those guys. We are trying to show that the set partition problem is polynomial time reducible to the subset sum problem, by which we mean that if somebody has shown that the set partition problem is NP complete, also that it is NP hard, then I have just shown you that the subset sum problem is NP complete, because this essentially means that if everybody can be reduced to SP, through our reduction we will reduce it to SS. What would your reduction be? Yes.
What if we take the same set and the x, we can take the sum divided by 2?
Ah, that is what you would do. Okay, so for those who haven't heard the answer, think for a moment. What would you do? So remember, you are allowed to produce any set. Don't start thinking that I am going to take the subset which sums to k, sums to the one side, and then do something with it. Well, you do not know the answer. Your transformation has to be such which is beyond the answer. The way I am thinking about this is I am saying, okay, so here is a set given. If there is a set partition, then I am going to pick out one of those subsets and it will add up to be something such that the remaining guys add up to be the same thing. That is the set partition problem. I am trying to transform this problem into the subset sum problem. What should I do? Should I take the same set? Let us try taking the same set. Assume in the first try I am going to take the same set and make S tilde the same set. I now have to produce the number x. Can you tell me what this number should be? Louder? Why should it be half of all the elements? You are basically saying that x should be the sum of all the elements divided by 2. Why is that? Because if it does have a partition, then this one would sum to something, the remaining would sum to the same thing. If you added this to that, that would be the sum of all the elements, and therefore you have found out what your x is. If you did not get this transformation, go to the book and try FU, because this is one of those very easy ones. So the way you go doing a polynomial time reduction from the set partition problem to the subset sum problem, which looks like is more general, is essentially to take the same x, same s, and x is simply summation of elements in S by 2. And now you go about proving that this is a valid transformation, because you say that assume that the answer here is yes. Then there are a bunch of elements there with sum to sum s over 2. We clearly know that the other guys have to sum to the same number. Therefore, this one has a set partition. That is going that way. And then you say assume that this has a set partition, then there are a bunch of numbers that will add to something, the remaining numbers would add to the same thing. Clearly, summation s over 2 is that, and so there exists a subset which sums to x. So now very clearly, this transformation is easy. This might be slightly more difficult. You can clearly see now what's happening, right? The subset sum problem, to try this reduction from the subset sum to the set partition, what is being said is that you will be given a set x, s and x, in this case only allowed to produce an s. This looks like it is more constrained, right? You will be given a set s, you will be given a number x, you have to produce a new set s tilde such that if this has a partition, this has a subset sum. Of course, in none of these have I told you that you need to also go and make sure that they are in NP, but yeah, don't forget that. How would you go about doing this one? So let me give you a picture of what's happening. Let us say that the answer to this is yes. Once again, remember, do not look for the answer. In the end, the transformation has to be something that does not choose the answer and do something. But if you do not think about the existence of the answer, you will not be able to solve this problem. Yes. Hold on. Okay, so you are given a subset sum problem. Here is a set, and it is turning out that I can pick up some of these and add them up to be x. I am assuming the existence of bunch of these numbers that add to x. Can I create a new set? Okay, I am not going to take the new set and just throw in new numbers. So, what I am going to do is I am going to take S tilde to be S plus something else, that something I do not know. I am going to throw in a new element, such that if there is a partition in that case, I want the subset sum to be picked up. Assume that this one has a partition. It has summed up all the elements and it is turning out to be exactly equal, and this additional element here is something that will have to be sitting on one side. So, here is your S, here is your additional element. When you add them all up, this side is equal to that side, and essentially that is the sum. Yes.
What if we add the additional element as an element in the set?
You are saying, can I add x to the set itself?
And try to find this equal x divided by b.
You are not going to try to find anything. All you are allowed to do is throw an element in and say, okay, here is your problem. Will that work? So, one suggested solution is take S tilde to be S union x itself. But you are there. You are now thinking. Okay, so you are going to play around. It will either be x or it will be something else. Once you get into the groove, you have already gotten into the groove. Now you know what needs to be done. It will just take you 15 more minutes maybe, or 5 more minutes maybe, and you will get there. But this thought process of going till here is what I find most people not being able to get. Soon as you know that this is where you are, and I just need to find that extra element, you will do some algebra on the right side. And you will figure out exactly which element to stick in there, so that a partition is going to give you the correct subset sum. And the lack of the existence of a partition will immediately say that there is no subset sum. I will not steal that happiness from you. I want you, after this class, to start from here and figure this one out. If you can figure this one out, then you know that you know how to do these things. Maybe you won't be able to solve the problem given in the exam in 10 minutes, but you know how to play these games. Okay, so I brought you to a point where the rest is for you to just carefully think and see what extra element you will throw in. Okay? And that pretty much ends all the topics that I could cover. Now, I know that a lot of you think that we have covered way too many topics. Unfortunately, we should run a little faster than what we have run. So, I wanted to cover a couple more things that I could not cover. Let me tell you now, because I don't want to be bombarded by emails. Things that I have not covered are not part of the exam. Okay, so I wanted to cover something called Huffman coding, which is essentially a way to compress strings. Okay, so let me give you a brief description of what it is. So, if you get text files, and if every letter in your text file is represented with the same bit sequence, then you know that the size of that text file is essentially going to be the number of characters in your text file multiplied by the size that you use to store each character. So, usually text files, characters get stored in 1 byte things, and so if you have 10,000 characters, you have 10,000 bytes. Now, it turns out that one of the simplest way to compress these things is to go and check and see whether there are elements that occur more often than other elements. So, if it turns out that your text file is full of A's and S's and B's, and you have very few Z's and Q's, a good idea is to find representation for these ones that occur very often to be smaller and the ones that do not occur very often to be longer. The way these things are essentially compressed is what you have is a little table on top which says when you see a 0 1, assume that it is an A, when you see a 0 0, assume that it is a B, when you see a 0 1 1 0 1 0, assume that it is a Z. See, Z does not occur very often, so I have this long representation for it. I put the table on top and then I code for the text below, and it turns out that these things turn out to be smaller. The coding that we use is something called prefix code, which is a very peculiar thing because prefix codes are codes which are not prefixes. Let me tell you what the problem is. Let us say that I produced for you some code, variable length. You now do not know where the code ends. See, if I told you that every letter is a byte, 8 bits, then you will count 8, pick that up and say, what is this letter? Then you will go to the next 8. What is that letter? What is that? And you will be able to decode the whole thing. But if I now told you that, well, I have variable length, then you do not know how long it is. So, there is one solution which says that I will put a stop character every so often. So, let us say that I will produce a new star, say, and I will say 0 1 1 star 1 0 1 0 star, and so on and so forth. Then you know that as soon as you hit a star, you have hit the code, the code, the code, and so on and so forth. The other one is this beautiful thing called a prefix code. A prefix code does not involve stop characters, and yet you can decode it. And the way you go about it is you keep looking for something until you realize that you have already hit a character. A prefix code is one where no letter is coded as a prefix of some other letter. Okay, so, let me show you what it actually means. Here is what is not a prefix code. So, this code is not a prefix code. The reason is that A is actually a prefix of B. If you did not have a stop character here, what would happen is that you would go this far and you would say I can either spit out an A, but I am not sure because if I continue, it might be a B. So, a code that does not land you in this problem, basically you can scan from left to right, and as soon as you see that you have hit an A, you immediately know that you do not need to continue because it is not going to be a code for some other character. Those are called prefix codes, and the prefix codes have a very easy representation also. Here is a prefix code, right? All leaves will have letters assigned to them. So, you start from the top. If you see a 0, you go left. If you see a 1, you go to the right, and you keep going down until you hit a character, and boom, you can spit that character out. A non-prefix code cannot be represented in this manner because you can clearly see A is on the path to B. So, in a tree where there are no characters sitting at any of the intermediate nodes is called a prefix code. The characters are essentially sitting just at the leaf level. Here is a prefix code. So, the idea behind Huffman coding was essentially, can you take a text file, scan, see how many of A's and how many of B's and how many of C's and so on and so forth, and based on that build us a prefix code that is going to compress well. It turns out to be a greedy algorithm, and it turns out to be optimal. So, if that is all you are trying to do, it is a very simple optimal greedy algorithm that gives you a prefix code for text files. Because I did not cover this, I just wanted to give you a brief understanding of what it is. You can read the book. It is not part of the exam. Please do not send me emails about it. Yes. Okay. Anything that I have not covered in the books, like more algorithms, say for example, if you look at network flows, we did Ford Fulkerson, but we did not do push relabel. New algorithms that I have not covered are not part of the exam. I will not ask you questions on push relabel. You can tell that there are more than enough questions out there for me to ask. It would be foolish for me to try to check you on something that I have not taught you. It does not mean anything. Somebody who has by mistake fallen on the wrong chapter might get the answer right. Okay. Somebody who has not attended lectures and has no clue what I taught might by mistake read push relabel and end up solving the problem. That is not my goal therefore. Believe me, and you all know this, there are going to be 5 questions and it is very easy to pick 5 questions. There is a whole fat book for me to pick from. I am not going to try to trick you. You will get questions that will cause you to think, and it will be in the domain that you already know. So, I have given you enough information about the domain, so that you can actually give it a shot. And remember, once again, it is only a 2-hour exam, right. You will again be tight. I keep telling you, but I mean it is not my place to tell you this, because I am not taking the exam. I tell you, do not get too stressed. Getting stressed does not help you usually. Think about the solution before you start writing. If you start doing stream of consciousness, all that will happen is 20 pages and nobody knows what is written in there. Think about the answer first. If you get a good clue, write it as small as possible, because it actually makes the TA happy. When a TA gets only this much and can grade it, the TA is happy. When the TA reads 2 pages and realizes you do not have the answer, the TA is unhappy. And an unhappy TA is not your best friend, because he or she is going to grade the next question and he is so unhappy with you that even though you have the correct answer, says, I am going to take a few points off. Usually it does not happen, but yeah, it is a good thing to keep it short. Let me quickly go over the list starting from the back side for you to realize that we have not covered that many things. We have covered a lot of stuff, but it is not that it is very overwhelming. Okay, so, we have NP completeness, before which we did longest common subsequence. Do you remember longest common subsequence? It was what most people call a dynamic programming solution to things. Of course, the clue was that if you start from one corner, you immediately get a recursive solution, which you end up producing a table with. Before that, we just did network flows. Okay, the max flow min cut theorem, the bipartite matching problem, which we found was a very nice application of network flows, but the basic idea was Ford Fulkerson. Before which we did a bunch of single source shortest path. Okay, you do not need to note these things down, because this is sitting on my website. So, whenever I cover something, I go and put it up there. So, we did all pair shortest path, which had this beautiful algorithm by Floyd-Warshall, if you remember. The idea was, do not try to look at the length of the hops to write your recursive solution. Remember, all of these were dynamic programming. So, the single source shortest path and the all pair shortest path both could be written down as recursive solutions, and so you needed an index. The index Bellman-Ford used was the number of hops in the path, and Floyd-Warshall came and said, what if instead of using the number of hops, we simply said you are only allowed to go through 1 through k, and the next time on 1 through k plus 1, and so on and so forth. That immediately shaved off a whole order V from your solution. The Bellman-Ford was covered just before that. it was a variation of the previous one, which was Dijkstra. Dijkstra very smartly managed to go and relax edges exactly once and get the solution. Bellman-Ford said, you keep relaxing over and over again. If you do it some number of times, which was V, you will find the right answer. The strength of Bellman-Ford is that Dijkstra cannot handle negative edges. Bellman-Ford can handle negative edges and can also come back and tell you that if there is a negative cycle, that there is no answer. So, there is a final test that comes and says there is a negative cycle, I have found it. Yes. Floyd-Warshall does not allow for negative edges, okay, because if you remember the proof, that is the reason why this course was very proof centric, right. An undergraduate course would essentially describe these algorithms to you and say just run these. Once you get to know the proofs, it tells you exactly what the constraints are for these algorithms to work correctly. So, if you look at Floyd-Warshall, I essentially said that the proof was dependent upon the following, that if you go through K, this segment will not go through K, this segment will not go through K, because that means that you go through a cycle. But if there is a single negative edge, that breaks it. So, Floyd-Warshall assumed that you had positive edges. Okay, before that, which was Dijkstra, I connected Dijkstra with breadth first search, right. So, the whole idea was that the breadth first search was also actually running a priority queue, it just did not need one and therefore could do it with a queue. Dijkstra essentially ran a priority queue. How many people here remember what a priority queue is? Okay, very good, okay, because you might get a question on priority queues, which happened way early in the semester. Okay, before that we did minimum spanning trees, Prim and Kruskal. If I describe both algorithms to you, will you be able to tell me which one is which? Okay, good. Okay, and that is where we started after midterm 2. Okay, so you'll get 5 questions, very likely 3 will be from this side, which means 2 will probably be from the other side. Okay, all these are likelihoods, probabilities. Okay, before midterm we had strongly connected components, topological sort, BFS, DFS. So, these were all graph theoretic algorithms that we did. We did red black trees. It is very unlikely that you will get a show me this rotation. Okay, computers do it better than you people do it, but it is a good idea to know that red black trees exist. If you ever get the need to implement one, if you just remind yourself that the whole idea was about balancing, and you can go through the list and you will immediately see that there were reasons for it to be done. It will probably take you a day and you will be able to remind yourself of red black trees. I do not expect you to remember how you do your rotations and stuff like that. So long as you know what a right rotation and a left rotation is, essentially taking nodes and rotating it and just moving the middle guy. Beyond that, you do not need to know much. Binary search trees, insertions, deletions, minimum, maximum, predecessor, successor, these were all very easy things. Before that, we did something which in my opinion was the most complex part of this course, which was the amortized analysis of the disjoint forest, okay, the one with the Ackermann function or the inverse Ackermann function. Before which we did a lot of amortized analysis. And before amortized analysis, so do you remember amortized analysis? If I asked you what the potential function is, would you be able to describe it to me? And how it is different from the accounting method? Okay. This is all I want you to leave this course with. I know that you go through courses and during that period of time, it is all in your head, and then you have this big gear, you can do this K-pop, right? You hit it and the whole thing pops out and that is it, you are clear. You are ready for the next semester. I am really hoping something will stick with you, because otherwise, I mean, there is one point to this, which is essentially you going and getting a job. Google really wants you to know algorithms, because when it asks you to code for something, they don't want you to be throwing in loops when you don't need to be throwing in loops. They don't want you to be doing bubble sort, because there is quick sort out there. But apart from that, algorithms is a field that should make you feel happy about every so often. It is very uncommon in the field of computer science. Okay, this is a very biased view on my part, but my feeling is that beautiful things happen in a subset of domains in computer science, and algorithms is one of them. I am not going to tell you the fields that I find do not have anything smart happening in it. In my opinion, there are, but that's just my opinion, and I will not tell you my opinion. Okay? But if 3 semesters from now you suddenly get told that there is this new algorithm that has come out for this particular problem, and if you just open it up as if you are reading a novel, that will be really good. Algorithms gives a lot of people happiness. You don't have to be a musician to appreciate music. Likewise, you don't need to be producing these big algorithms to actually appreciate the beauty of these things. We did a bunch of lower bounds. These are reductions. Those were reductions. I would like you to think about how this reduction and that reduction connects. If you remember long back, I asked you this question about, can you show that I can move a lower bound? What I did was I said that, okay, we have proved a lower bound for sorting. Do you remember the lower bound for sorting? Okay, good. Decision tree based lower bound for sorting. And then I said, well, here's this new problem where I am going to want you to list points in counterclockwise or clockwise. And I asked you, can you prove a lower bound for this? And you showed that if you transformed the sorting problem to this problem, what you basically said was this problem was at least as difficult as the sorting problem, and therefore, if you have a lower bound for the sorting problem, you have a lower bound for this. This is the same thing. It says that this problem is at least as difficult as this problem. That is where the greater than equal to sign, that is what it essentially means. Both reductions are the same. If you have lower bounds, you can push lower bounds to the other side. If you do not, you basically talk about being NP complete. And before this, we did a bunch of heaps and sorting. Okay? And that is all that we did in this semester. So, yeah, before I close, any questions? Any questions about anything? Do you want to know why the market is moving up and down? I strongly suggest, a lot of you out here probably are drawn towards finance. I know that there is a lot of money that is made in finance. I strongly suggest that you pick up a couple of books. So both of them are written by a guy called Michael Lewis. There is one that has come out recently called Flash Boys. One that came out a little earlier called The Big Short. These are novels. These are historically placed novels. I think he claims that whatever is written out there actually happened. You will enjoy it. You will get an idea of what happens in the domain of finance. I keep getting this question all the time. What does algorithm have anything to do with the domain of finance, where in a year's time you can make 10, 15, 20 million dollars? Okay? Read these books. They are good novels. Historical novels. They are also New York Times bestsellers. So, you know that they will be interesting reads. Any questions about any other courses? Okay, so if that is the case, let's stop. We'll be back here Monday. I will be happy, you will be sweating. But after Monday, it will all come to an end, and hopefully you will remember this as a good course. Okay? I had a lot of fun teaching. I hope you had, at least setting aside the assignments and the exams, you had fun too. Okay? We'll stop here.